Hello, this is Suzanne Russ. I am going to talk about cautions and interpretations when it comes to correlations. So we know already that correlations use continuous variables. We'll just distinguish this. Nominal variables are variables that differ by name only. So the categories differ by name. So for example, hair color, red, white, blue, green, yellow, black. Those are just words. And so the categories differ just by name. And so hair color is a nominal variable, and it doesn't matter what order we list those colors in. The same for favorite pizza topping. We can list the ingredients in any order, it doesn't matter, or type of car owned. In each case, the answers to the question are words rather than numbers, and the order doesn't matter. We don't use these for correlations. We only use the continuous variables where data fall any place along a scale, like weight or height, hours of screen time, level of extroversion, number of siblings, and so forth. Now, if you're watching this outside of class, you'll want to maybe take a moment and see how well you're understanding it. Could we use the following variables for correlation? And so let's just imagine that these are the variables. Could we use outgoingness? Could we use hours of employment? What about eye color? And so if you look down this list of variables, you would see which ones are continuous and which ones are not. And we might consider this ordinal, but we're using it as continuous in our data set. So you should do this on your own, and then you can look at the answer key on your own time. So we do have some issues that emerge when we're interpreting our correlation coefficient. And one of the biggest problems is what we call outliers. We'll look at this in a moment. And these are number pairs that are really far outside the cluster of data points. And those will really pull the correlation coefficient off. We'll look at why in a moment. Then range restriction. If we end up with a cluster of values on the high end or low end, such as we're plotting test scores and a whole bunch of people got perfect scores, then we're going to have a funny correlation coefficient if we try and work with the data. Those clusters tend to throw off the correlation calculation. And then we always know garbage in, garbage out. If one of our variables has poor data, is unreliable, then the correlation coefficient will be off. And I won't go through the example. And then, of course, nonlinear relationships. If we're trying to fit a model that is not linear using the Pearson formula, we're going to have a weird number in there too. So let's take a look at some of these. And the biggest one is outliers, points that don't fit the pattern. And you can see in this first example a nice clear cluster of points, except, oh no, we've got this cluster over here. We have to draw a line that's close to them too. So we end up having to move our whole line over. Now, in order to capture the data in those, we have to go with a line that's something like this. And you can see that our strength is really going to be compromised because we have a cluster of points and then some that are really pulling it off. So we're going to have a lot lower strength there. And here's another example of an outlier. We have an exam score, midterm exam score, and a final exam score. And for the most part, people's scores were similar. If they did really well on the midterm, they probably did really well on the final. If they did poorly on the midterm, they probably did poorly on the final. But look at this person who did very poor on the midterm, but very well on the final. Maybe he was sick the day of the midterm or something like that. Whatever was going on though, that point is an outlier. Does that mean we can throw that point out? No, absolutely not. The only way we could throw it out is if we could in fact demonstrate that this person was not part, was very sick on the day of the third exam, wasn't part of the typical population who took that exam. then we could build a case, but we'd have to examine each point individually in order to make such a decision. The data tells the story, and we can't arbitrarily throw out points because they're inconvenient. Now here's an example. This is kind of a nice one. Look at where the line of best fit is. This is a correlation of r equals 0.4 because of this outlier, because we have to get the line closest to all of these points so the outlier really increased the distance. Now, if we did in fact find that this person was not a member of the population, then we move it, and then look what we have. This line right here. Now we have a much stronger correlation. In this example, I did show you a bunch of pairs of data and ask which one you think might be the outlier if you were going to plot these points. It really is asking you to imagine the points, and I'm not even going to go through it just now because I don't think it's as clear as I would want it to be. So we're going to come to a different example in our class. If the relationship is curvilinear, then we can't use the Pearson R statistic. There is a different statistic. Your book talks about it, but we're not going through that in our class. But what it does is it rank orders the pairs so that we're using the ranked scores instead of the original scores. We're not going to do it. Now, the idea of this range restriction, where a lot of points are cut off, so here's the range. Now imagine that all these points, because the range was that low, all these points are going to be clustered around this lower end. And you can imagine that there's a lot more points now. They're going to pull that correlation off if we truncate that data set. Truncated at the low end, a floor effect, or at the high end, a ceiling effect. You can see the R value is a 0.91 when we have these points here, but when we cluster them all around here, our correlation coefficient gets much weaker. The last thing that's very important is what we call interpreting correlations. And the reason this is so important is because it's so often made by mistake. And so, for example, this is a headline, Facebook causes depression in teenage girls. It's based on a correlation study in which teenage girls were surveyed about how much they use Facebook and how depressed they were. And the correlation was significant. But this interpretation that Facebook causes depression is in error because we actually don't know. It could be, first I'm going to show you here, and then we'll look at this on the next slide. It could be, it's plausible that Facebook could cause depression. You know, people go on Facebook, they compare themselves with their peers, you know, it doesn't look good, they get depressed. But it could also be that depression causes people to use Facebook more. They're depressed, they're staying home, they're not hanging out with their friends. What are they doing while they're staying home? They're scrolling through social media. Or it could be some unknown factor that we haven't included in our study that both causes girls to be on Facebook and causes them to be depressed. And maybe it is something like neglectful parents don't monitor their kids' social media use. And also, the kids need attention, so there's a greater likelihood of depression. So this would be what we would consider a third variable. Let's look at this again. So to look at what we just went over, the big picture is why we can't draw causal conclusions or why correlation does not equal causation. It's because the relationship between variables in a correlation has 3 or even more possible explanations. The first of these we name the expected cause effect. You should learn this language, and it just means X could cause Y. In the example we just gave, Facebook use, variable X, could in fact cause depression, variable Y. And we might ask, is this plausible? And I'd say, yes, it's plausible. We could cause girls to compare themselves unfavorably with others. But however, that's not the only explanation, because the reverse cause effect is also possible. Maybe variable Y caused variable X. Is this plausible? is it plausible that having depression, Y, might cause a person to go on Facebook a lot, X? And I say, yes, this is plausible because they have withdrawn from other activities. Finally, a third variable that we haven't considered could cause both X and Y in a systematic way. For example, such a factor might be parental neglect, which might cause a person to both feel depressed, which is variable X, and also escape into Facebook a lot, variable Y. So that would be plausible as a third variable. Therefore, causal conclusions may not be drawn from correlational findings. Here's another example of misinterpretation of correlational finding in the headline. This headline reads, "Happiness wards off heart disease." This phrase, wards off, suggests that becoming happy could somehow prevent heart disease. And they even say as much in the first sentence of the article. And maybe it's true, but we can't draw that conclusion from a correlational study. Why not? We have our three possible alternate explanations. First of all, we could have it the way the headline reads. The expected cause effect, X causes Y. A person's level of, or people's level of happiness could cause the heart to be healthier. Why? Because it might activate beneficial hormones that help with heart health, something like that. But it's also possible that the reverse cause effect is true. Well, we'll see if it is. Could variable Y cause variable X? Could having a healthy heart cause people to feel happy in some systematic way? I'd say maybe so, right? Because maybe they're looking around and seeing their friends looking less healthy and they are healthy, and maybe that makes them grateful and happy. We could also have a third variable, some unknown factor that we haven't considered that causes both X and Y. And so this third factor, I can think of one, maybe exercise. Exercise might both cause a person to feel happier, we know it has that effect, endorphins, and at the same time reduce the risk of heart disease. Why? So maybe exercise rather than happiness is the factor. And when we misinterpret these correlations, there's possible problems because, people might not recognize the role of exercise if that's the factor. They might think it's all about just getting happy, so they might indulge themselves a lot because it makes them feel happy and think that that would bring them heart health. And so we do have to be careful with these interpretations. In this final study, this is an article I clipped from the Green Bay Press Gazette some years ago, and it's giving the results of a correlational study saying that raunchy sex lyrics prompt teens to start having sex. And again, this is just the result of a correlation, which found that teens who listened to music with more raunchy sex lyrics were also reported in the same survey that they had sex at an early age. The more they listened to those lyrics, the more likely they were to be engaging in promiscuous sex. Or not promiscuous, I should say, but sexual engagement at an age when they're might not ready for it. And you don't have to read the article. We're just looking at the headline. And so it might be that you can answer this. Is the expected cause effect possible? X causes Y. Is it possible that listening to raunchy sex lyrics makes teens more likely to start having sex? Is that plausible? So you can think about that. Is the reversed cause effect plausible? Y causes X. Is it possible that getting sexually active causes teens to start listening to music with raunchy sex lyrics? Maybe that's also plausible. Or is there some third variable, something we haven't thought of, that both causes teens to listen to music with raunchy sex lyrics and to become sexually active? So you can think about that for a moment, and on your own, you can look at the next slide explaining those relationships.